Hello everyone and welcome. My name is Jiaqi Zhang, a senior software engineer at Alibaba Cloud. Today, I'm excited to talk about building AI context engineering with Serverless AnalyticDB for PostgreSQL. Our journey today will cover 4 sections. First, we will get an overview of AnalyticDB for PostgreSQL. Then, we will dive into its architecture revolution as it moves towards serverless and storage compute decoupling. Following that, we will explore AI context engineering solutions, focusing on making our database AI ready. Finally, I will provide 3 demos, especially AnalyticDB Supabase. Let's start with the basics. What is AnalyticDB for PostgreSQL? Our product is an online massive parallel processing data warehousing service. It's fully compatible with GreenPlum, PostgreSQL, and Oracle syntax. This is a cloud-native database service offering high flexibility, scalability, and high performance. Importantly, it also provides a high-performance vector database feature, which is crucial for modern applications like retrieval augmented generation, or RAG, and other generative AI scenarios. This figure presents a capability overview. In addition to the traditional data warehousing capabilities, AnalyticDB offers 2 vital capabilities. The first is a robust vector database for storing and querying high-dimensional embeddings. And the second is a seamless integration with a broader Model Studio ecosystem. This synergy provides a comprehensive platform for the entire AI lifecycle, from data processing to model serving. This slide presents the performance overview. While I won't go into specific numbers today, the figures have demonstrated that our product has achieved outstanding performance across various data processing tasks, including the TBC-H and the vector retrieval. Our product addresses several typical business scenarios. First, for real-time warehousing, data from RDS MySQL, SQL Server, or PostgreSQL can be synchronized in milliseconds using DTS. It enables real-time data analysis. Secondly, it's excellent for big data and AI platforms. The data from Max Compute or Hadoop can be loaded for interactive queries, and vector data can be easily processed for AI-ready applications. Lastly, for data lake operations, it enables high-performance analysis of OSS data through parallel reads. Now let's look at how AnalyticDB for PostgreSQL is evolving through its architecture revolution. It moves towards a serverless model and true compute and storage decouple. So why do we need serverless? As shown on the left, the rise of generative AI has triggered an explosion in data and storage demands. It requires solutions that are both more cost-efficient and highly scalable. Meanwhile, cloud data warehouse workloads are inherently dynamic. Figure on the right illustrates the typical CPU usage pattern of an online AnalyticDB instance. It highlights how traditional, the tightly coupled architectures struggle to adapt. Our serverless architecture revolution directly tackles these challenges. This slide demonstrates the architecture revolution. We move from the isolated AnalyticDB for PostgreSQL instances with local ESSD to the decoupled design where the storage is handled by the dedicated storage nodes backed by OSS. This separation allows compute and storage scale independently, reduces storage cost, improves data durability, and simplifies maintenance and failover. In practice, it means faster scaling, lower storage cost, and easier upgrades while keeping PostgreSQL compatibility and performance. On this slide, we present our new architecture, which decouples compute from storage into modular layers. The compute nodes run serverless AnalyticDB PostgreSQL instances, we can see it includes both the master and segments, and the storage responsibilities are handled by components, including log keepers, page servers, and remote OSS-backed object storage. Built on this shared storage, we can offer Supabase services and advanced capabilities like virtual warehouses and database branching. They involve independent scaling, stronger durability, and simpler operations. The shift to serverless brings significant advantages. The first advantage is the cloud-native and compute storage decouple. It allows independent resource allocation and second-level resource scaling. The second advantage is the high performance price ratio. With a shared storage and a pay-per-use model, you only pay for the compute when it's active, leading to substantial cost reductions. The third advantage is the scheduled scaling and auto-scaling. We are now supporting time-based scaling and instance pausing. The last advantage is the data sharing. We are now enabling real-time data sharing between different AnalyticDB Postgres instances. Next, let's move on to our third section. In this section, we explore AI context engineering solutions and how we are building an AI-ready database. Here, I will outline our AI context engineering stack and demonstrate how it addresses 4 core challenges of AI context engineering through a so-called all-in-one AI stack. First, the serverless AnalyticDB for PostgreSQL natively handle tabular, image, video, and vector formats to provide a unified, efficient storage and information retrieval. Second, a dedicated vector database, together with InDB AI, moves search and AI inference closer to the data. It accelerates retrieval and simplifies application workflows. Third, we are providing database service and database branching capability. These capabilities are designed for vibe coding and let the development teams experiment and iterate without heavy infra coding. On this slide, we present our vector database solutions that power IG and improve data transmission. Our platform combines vector search with full-text search and circle, delivering 2 times to 5 times higher performance and the ability to involve billions of vectors per search. It integrates zero-ATL with AnalyticDB and supports data sources such as PolyDB, RDS, and Lindo. Together, these capabilities enable fast, scalable IG applications and a better user experience for enterprise generative AI deployments. On this slide, I will introduce InDB AI on AnalyticDB. It integrates model training, fine training, and distributed inference directly inside the database. It supports frameworks like PyTorch, TensorFlow, and common large language model libraries. By moving the vector and feature processing to the data layer and exposing capabilities through standard SQL, we eliminate network overhead, accelerate retrieval, and simplify pipelines. The result is high performance, low cost ML deployment with strong security. That is, the data never leaves the database, and the data access is always controlled. It makes AnalyticDB ideal for production large language model and real-time AI workloads. Next, on this slide, I will introduce Graph IG of AnalyticDB. The traditional IG often falls short when questions require complex relationships, multi-hop reasoning, or knowledge association. They always lead to shallow, fragmented results. The Graph IG fixes this by combining a vector database with a graph database. We extract entities, relationships, store them in AnalyticDB, and retrieve by traversing the graph to assemble a focused context. The large language model receives connected evidence and returns answers that are more accurate, coherent, and explainable. To be simple, GraphIG transforms the isolated chunks into a linked knowledge network, delivering relationally rich responses for practical and real-world tasks. Next, let me introduce AnalyticDB Supabase. The Supabase is an open-source backend as a service product for the web coding. Deployed in Alibaba Cloud, now each user can create up to 2 instances for free. We use this slide to contrast the traditional development with AnalyticDB Supabase. Traditionally, the developing teams have to maintain auth databases, storage, and edge functions separately. Then they also have to manage engines, domains, and CDNs. With AnalyticDB Supabase, these pieces come pre-integrated. A Postgres-compatible database, secure auth and login pops up, as file storage and serverless edge functions, all behind a managed gateway. Your front end connects through the database client and MCP server, and the platform handles scaling and reliability. Web coding boosts productivity. It also introduces data security concerns. To address the concerns, we will provide the database branching capability. Powered by our cloud-native storage engine, it allows developers to create isolated database branches for experimentation. For example, in this figure, when we are developing an app, we can build a database branch. Then we can also perform DDL changes, like dropping databases. This will not affect the main production database. If you are not satisfied with the app version after the DDL operation, you can easily go back to the main database and build a new version app from a new branch. Now let me show 3 live demos for AnalyticDB Supabase. Here in the first demo, we present some basic functions of AnalyticDB Supabase through an MCP server. First, you can see we can easily deploy the MCP server on cursor. And next, we can ask the AI agent to do some actions, such as we can list all Supabase projects from a region. And next, I ask the agent to create another Supabase project, the inventory. And after the creation, I ask the agent to create a test table inventory, and also it will mock some data in the table. After generating the circle and after the circle execution, looks like the execution is done. And let me check the dashboard, and we can see the data is here. The next demo highlights a truly powerful feature, the database branching. Here you will see after we build a new branch from our main database, we can check the Supabase of the new branch, and the data of inventory is here. And we are trying to do some destructive operation, such as drop the table. And after the execution, the data is gone in the branch, and the data is still here in the main database. For our third demo, we are showcasing how to develop applications with AnalyticDB Supabase. In this case, we are developing a Flutter application running on iOS simulator. You can see the development is with a web coding tool, Cuder. The Cuder's AI agent does not only build the app, but also interact with the Supabase. In this case, our target is to develop an image editing feature with the large language model. Specifically, we achieve this by deploying an edge function that calls APIs from large language model services. And in this application, after setting up, we are trying to run the app and upload the image and edit the image by changing the dog to cat. The task is finished in a second, and we can check the record in the Supabase dashboard, and we can see the uploaded image in the storage bucket. In summary, AnalyticDB for PostgreSQL is evolving rapidly with its serverless compute storage decoupled architecture. It's becoming an AI-ready database, offering robust vector database capabilities in DB AI, GraphIG, Supabase, and features like branching to empower AI context engineering and secure development. This is the end of my presentation. Thanks for your time.